Good morning to everyone. Today we are going to learn a new topic named enthalpy of a system. As we are going to learn thermodynamics in this chapter, so enthalpy of a system we should learn. Enthalpy and the internal energy, they are very similar term, however there is some significant difference. So we will learn what is enthalpy, and then we will try to learn enthalpy, a state function. In one of the previous class I have mentioned about the state function. Today I may give you some reminder. However, we should explain the enthalpy as a state function. Then we will try to find out the change in enthalpy, how we can calculate the change in enthalpy, then units and sign conventions of enthalpy. So what are the signs or the units for the enthalpy? Then we will try to see what is the relation between delta H and delta E. That means delta H is the change in enthalpy and delta E is the change in energy or internal energy. So what is the relation? Already I have mentioned that they are very similar, the enthalpy and the internal energy quite similar. However, there is some significant difference. So we will see what is the difference. So I want to So let us start from the beginning. What is enthalpy of a system? Say you need to remember an equation that will give you the definition very easily. Here you can see an equation H equal E plus PV. So if you can remember this equation, then you can easily define the enthalpy. So the total heat content of a system at constant pressure, the total heat content, what would be the total energy or total heat content of a system at constant pressure equivalent to the total internal energy, equivalent to the internal energy E plus the PV energy. That means if there is some work done by the system or on the system due to change the volume, so the total heat content or the enthalpy, this is the actually we should mention that as the enthalpy. That means the total heat content of a system at constant pressure. That means if you have a system which works at constant pressure, that means if you increase the internal energy or if you supply some energy, in that case the pressure will remain constant, so that it can increase or decrease the volume to perform some work. So if the total internal energy or what the total heat content of a system at constant pressure would be the equal to the sum of internal energy plus the PV energy. PV energy, that means the work energy due to the expansion or compression or change in volume. So if you can remember this definition or this equation, then you can easily define the enthalpy of a system. So just need to think about, if you do not have any work done due to expansion, that means no volume change. If you have no volume change, that means in that case delta V would be 0. So no work done due to change in the volume. So that time we will get this term 0. In that case you will see H equal E. That means the total heat content and the total internal energy will be exactly the same. So for that reason I have mentioned that enthalpy of a system and internal energy of the system, in some sense it is similar or same. So, if you have the condition there is no work done by the system or on the system due to the expansion or compression of the volume. So, if you do not have any work performed for the system or by the system, in that case you can have no work done, that means this term will be vanish and you will have only this term and this term. So, delta H or H equal E, just what would be the enthalpy of the system would be equal to the internal energy of the system. So, in a process carried at constant volume, say in a sealed tube, the heat content of a system is the same as internal energy. So, there is no volume change, as I have mentioned. If there is no volume change, the internal energy would be the exactly whatever we can find here is. So, as no PV work is done, but in a constant pressure. Constant pressure, that means if you need to have a constant pressure, that means you are applying some energy to the system. What will happen? The pressure should be increased, because if you increase the internal energy, in that case what will happen? The molecules will try to move very fast, that means the kinetic energy will increase, but you will not allow to increase the pressure. Then what will happen? You need to either increase the pressure, volume, you need to increase the volume or decrease the volume. So, if you take out some energy, in that case you need to compress the volume, or if you insert some energy, in that case you need to increase the volume. So, in that case there will be some work done for the system or by the system, or just due to some change in volume there will be some work. So, but in a constant pressure process, the system, a gas also expands energy in doing PV work. Therefore, the total heat content of a system at constant pressure is equivalent to the internal energy E plus the PV energy. This is called the enthalpy. So, the enthalpy equal E plus PV. So, just remember this equation, then you will be able to define the enthalpy of system, and you can understand when the enthalpy and the internal energy will be same, because if you have this term is 0, how it can be? Just if we have the delta V or V, that means no change in volume. So, delta V equals 0, in that case this term will be vanish and you will have just the H in the right hand side. So, the E in the right hand side. So, H equal to E. So, the internal energy and enthalpy will be equal. Enthalpy, a state function. So, first of all, just I am going to remind you what is the state function. A thermodynamic system is said to be in a certain state when all its properties are fixed. Temperature, pressure, concentration, number of moles, whatever. This, if you have a thermodynamic system, is said to be in a certain state. If you have a solid, liquid, gaseous or whatever. So, a thermodynamic system is said to be in a certain state when all its properties are fixed. That means, if you consider for water, you can think about temperature 20 degrees Celsius, volume 1 liter and the number of moles or mass 1 kg or 1 liter, that means 1 kg corresponding to water. So, the pressure, if you consider for the atmosphere, so you can consider 1 atmosphere pressure. So, temperature 25 degrees Celsius or 20 degrees Celsius and the volume or mass is 1 kg or 1000 milliliter or 1 liter. So, these terms are fixed for if you want to define a system. So, a thermodynamic system is said to be in a certain state when all its properties are fixed. So, what are the fundamental properties? Already mentioned that pressure, temperature, volume, mass and composition. That means composition, that means what are the components present in the water, oxygen and hydrogen. So, for any other system there will be several components, you can have different several components. So, you need to fix all the composition. So, I have mentioned that water, 1 liter water, but if I have said that about 1 liter mixture of water and salt, in that case you have two different components, water and some salt. So, you need to mention the composition to define the system in a certain state. So, since a change in the magnitude of such properties alters the state of the system, that means if you change any of the properties, that means if you change the temperature of that water, what amount of water I have mentioned, 1 kg or 1000 milliliter or 1 liter water at 25 degrees Celsius. Now, if you change the temperature of water to less than 0 or minus 5 degrees Celsius, in that case the state already changed, because now it will be at ice state. So, if you change any of the fundamental properties, here we have mentioned the fundamental properties. So, since a change in the magnitude of such properties alters the state of the system, these are referred to as state variables or state functions or thermodynamic parameters. So, these are the state functions. So, if enthalpy is a state function or not, let us see. In equation 1, that means this equation. So, here you can see we have the internal energy plus PV energy or PV work done energy. So, enthalpy. So, if enthalpy is a state function or not, in this equation we have found enthalpy equal to internal energy plus PV energy. Okay. Equation 1 above E, P, V all are state functions. So, here energy, internal energy, pressure, volume. So, if all of them are state functions, so any quantity or any parameter who is directly related to these parameters, definitely that should be also a state function. So, if you have anything related to that parameters, in that case the overall system or overall quantity must be a state function. So, thus H, the value of which depends on the values of E, P, V, must also be a function of a state or a state function. So, hence its value is independent of the path by which the state of the system is changed. So, just remember, if enthalpy of a system is a state function or not, as we have defined that H equal E plus PV. So, we know internal energy, pressure, volume, all of them are state functions. So, any quantity or parameter, if it depends on some state functions, definitely that quantity will be another state function. So, enthalpy is a state of the function or a state function. Okay. Now, how we can calculate the change in enthalpy? Just if you have a system, then actually we cannot calculate the enthalpy or a specific enthalpy of a state or a system. So, most of the time we try to find out the change in enthalpy. If delta H be the difference of enthalpy of a system in the final state and initial state. So, this is the final state and the initial state. The initial enthalpy H1 and in final enthalpy H2. Then we can write down, sorry, just a second. স্যার ক্লাস নিচ্ছি স্যার 11টা পর্যন্ত। হ্যাঁ আচ্ছা আচ্ছা হ্যাঁ আচ্ছা 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 ঠিক আছে স্যার। ওকে ওকে থ্যাংক ইউ। Sorry to disturb you. What is this? Okay, we are going to calculate the change in enthalpy. If you have two different states, or if you have the enthalpy of two different situations, initial and final, so delta H equal H2 minus H1. So initial enthalpy and final enthalpy. So just already we have found that the equation here H equal E plus PV. So if we consider the initial, that means H1, let us consider initial enthalpy for a system H1, then we can write down H1 equal E1 plus PV1 or P1V1, like this way. Let us see. So delta H, first consider H1, H1 equal E1 plus P1V1. Just we are representing all the terms initial energy E1 plus initial pressure plus into initial volume. So E1 plus P1V1 equal and H2 we can represent in the similar way, E2 plus P2V2 equal. So now if we organize the equation like this way, just we are bringing together the energy term E2 minus E1. Pritin, what you can say?
Sir, what is H2?
H2?
Yes.
Final is enthalpy, final state. We have considered two different. We want to find out the change in enthalpy. So we have considered the two enthalpy, initial state and final state. So final state, the enthalpy is represented by H2 because we have mentioned that we are going to represent enthalpy as H. So initial as H1 and final as H2. That's simple. So we are writing the delta H equal H2 minus H1. What is the change in enthalpy? Just delta H. Delta H equal final enthalpy minus initial enthalpy. So now if we put the value for H2 and H1 like this way, as already I have mentioned, H2 we can represent H2 equal E2 plus P2V2, and then H1 equal E1 plus P1V1. So now we will bring the similar term together, that means E2 minus E1, so E2 minus E1 and P2V2 minus P1V1. So P2V2 minus P1V1. So now we are getting, write down, you can E2 minus E1, that means you can write down delta E, just change in the internal energy of the initial state and final state. Similarly P2V2 minus P1V1, that means delta PV, just PV minus P1V1, sorry, P2V2 minus P1V1, we can write down delta PV. Just so if P is constant, so if P is constant, so we can write down that this is delta P. We have written here delta P, P2 minus P2V2 minus P1V1. So we have written delta PV. Now if you think, or if we consider the system is isobaric process, that means the system is in constant pressure. So if P is constant while the gas is expanding, we can write, then now you do so delta P will be in terms of P, no delta P, just it will be just as a P constant pressure. Now delta V, so it will remain the only delta V. So the final equation becomes delta E plus P into delta V. So P into delta V, we are getting delta H equal delta E plus P into delta V, or delta H equal delta E. What we have mentioned in last class, we have mentioned that the energy, that means P into V or delta V, that means the work done, PV work, that is actually the PV work, we can represent by W. So delta H equal delta E plus W, that is the equation what we can say. So delta H equal delta E plus W. This is the according to the first law. In the first law of thermodynamics, we have mentioned that delta E equal Q minus W. Yesterday we have learnt about the first law of thermodynamics. They are mentioned that delta E equal Q minus W. That means the change in internal energy equal to the supplied energy minus the work done, where Q is the heat transferred, how much energy we are supplying to the system to perform the work or whatever is equal. So another delta E is the change in internal energy or change in energy minus the work done, how much work it is done. So due to the expansion or change the volume. So from equation 3 and 4, this is our equation number 4, and previous one, this is equation number 3. So delta H can be written as delta E plus Q. So what we want to write down? Okay, just we want to write down delta E in terms of, so delta Q minus W equal delta E. So if we equivalence delta E Q minus W, so you can write down here delta H equal delta E Q minus W. So W become cancel out, minus W plus W. So we have only delta H equal delta E. So you can see delta H equal Q or delta H equal, so from the equation 3 and 4, delta H equal Q, when change in state occurs at constant pressure, this relationship is usually written as delta H equal QP, where subscript P means constant pressure. So the enthalpy change of a system is equal to the energy transferred or heat transferred to the system at constant pressure. That is the enthalpy change we can easily calculate. Thus delta H can be measured by measuring the heat of a process occurring at constant pressure. What time? Okay, still not started, but they given units and sign conventions of enthalpy. Since delta H equal H2 minus H1, so what is the sign and the units for this term or enthalpy? So we know that delta H, or we can consider easily, if you need to find out any difference or you need to find out final to initial, just subtract. If you find out any displacement, just initial distance, initial position to final position. So similarly we are counting the change in enthalpy, just H2 minus H1. So delta H is positive if H2 greater than H1. This is very simple. So that means if the final enthalpy is greater than initial enthalpy, delta H is positive. So and the process or reaction will be endothermic. That means for any system, if the H2 is greater than H1, that means the final enthalpy is greater than initial enthalpy. In that case, the system will be, the sign of the delta H will be positive and the reaction is, or the system will be endothermic. Now you can easily consider for a endothermic reaction, actually what happens? For endothermic reaction, you need to provide some energy to happen the reaction, and exothermic reaction you need to automatically it generates some energy. So, for an exothermic reaction, the H1 is greater than H2. That means the initial enthalpy is greater than the final enthalpy. Okay, I have 5 more minutes, so I have another meeting with some other head of the department of CSE, so I need to join there. So I will continue just up to 5 minutes. In the case of chemical reaction, so I have mentioned that endothermic reaction when if the H2 is greater than H1, so H2 is greater than H1, that means the delta H is positive and the reaction is endothermic. That means the exothermic process, for the exothermic process, the delta H, so not delta H, I would say this is the heat is evolved. For the exothermic process, the heat is evolved, but the enthalpy, that means delta H is negative. So, for H2 greater than H1, the process is endothermic, and if H1 greater than H2, then the reaction is exothermic. In case of chemical reaction carried in the laboratory in an open vessel, so if you have a system, that means you are performing some chemical reaction in an open vessel, that means the pressure of the system is almost constant, 1 atmosphere. In that case, you can consider just the volume will increase and the pressure will remain atmosphere or constant. So, we can consider that system as in constant pressure. So, the heat of the, in the case of chemical reaction carried in the laboratory in an open vessel, delta H equal H products minus H reactants. So, QP, that means the heat of reaction at atmosphere pressure is usually shown along with the equation. So, hydrogen plus oxygen, if you write down the reaction like this way, hydrogen gas, 1 mole of hydrogen gas reacting to give half mole of oxygen gas to form 1 mole of water, liquid water, and delta H equal 68.32 kilocalorie. That means for this reaction, the quantity of heat 68.32 kilocalorie on the right hand side represents minus delta H. That means delta H is positive actually. So, H2 greater than H1. No, I did mistake. The quantity of heat 68.32 kilocalorie on the right hand side represents minus delta H of the reaction, because the reaction is, in this reaction actually exothermic, because half mole hydrogen and 1 mole hydrogen and half mole oxygen reacting to form 1 mole of water, and that gives the exothermic energy or some heat is produced. Delta H is actually negative. Here we did not put any sign, but we want to mention that this has some change in energy. So, the quantity of heat for 68.32 kilocalorie on the right hand side represents minus delta H of the reaction. The units of delta H are kilocalories, or you can consider kilojoule, just exactly similar to the energy, because enthalpy is also one term of or one type of energy. Therefore, it should have the energy or the unit joule or kilojoule or kilocalorie, exactly the similar what we have the unit for the work or energy. So, this is the end of today's class. I have to join another meeting. Thank you very much. See you in next class. If you have any question or comment,